Hello, Pre-Calc Excel students. Welcome to Lesson 2.6 on rational functions. What we're going to look at in this section is how to graph rational functions. So here's the standard form of a rational function. N of x represents the numerator. Okay, so we have a polynomial in the numerator, and we have a polynomial in the denominator, which we're calling d of x. And d of x, of course, cannot equal 0. For the rules that we're going to lay out, it's important that n of x and d of x have no common factors. The domain, remember for a rational function, the domain is all values except for the ones that would make d of x, the denominator, equal to 0. The zeros or x-intercepts, they occur at the zeros of n of x, the numerator. Asymptotes. So we're going to define both vertical and horizontal. A vertical asymptote, if as x approaches a, from the left or right side of a, and f of x approaches infinity or negative infinity, then x equal to a is a vertical asymptote. So what we're saying is that if you have a value of x whereas the function values approach it, they soar upward or downward. Then if this is x equal to 2, the line x equal to 2 is a vertical asymptote. And again, those occur at the zeros of the denominator. For horizontal asymptotes, if f of x approaches b as x approaches infinity or x approaches negative infinity, then the line y equal to b is a horizontal asymptote. So right here, we could use this dashed red line as an example. Okay, so if I continue these graphs, what we're saying is that our function values are approaching whatever this value of y is. If this is the x-axis, then it would be as y is approaching 0. Okay, on either side, as x approaches infinity or negative infinity, that makes this line y equal to 0, or the x-axis, a horizontal asymptote. Okay, so now there's different rules for the horizontal asymptotes. What we're going to do is compare n and m, which are the degrees of the two polynomials. N is the degree of the numerator. M is the degree of the denominator. So if n is less than m, then y equal to 0, or the x-axis, is the horizontal asymptote. If the degrees are equal, then y equal to the leading coefficients, a sub n over b sub m, is the horizontal asymptote. If m is less than n, then there is no horizontal asymptote. And we'll get to what happens in that case. So again, it's all about comparing the degrees. Okay, so if n is exactly 1 degree higher than m, then we have what we call a slant asymptote. So this was the last case where the numerator had a larger degree than the denominator. We said there was no horizontal, but there is what we call a slant asymptote. We find the slant asymptote by doing long division. We divide the denominator into the numerator, and y equal to the quotient is the equation of that slant asymptote. And for our purposes, we can disregard the remainder of that division. So it's just y equal to the quotient. So things to keep in mind. The graph of a function, it may cross a horizontal or slant asymptote, and that would occur in around the origin, if you're going to see that, not out at the extremes. But it will never cross a vertical asymptote. Remember, that comes from the zeros of the denominator. Those are the values that are not included in the domain. A graph can have numerous vertical asymptotes, but only one horizontal or one slant, and never both at the same time. Because remember, they depend upon the degrees of the numerator and denominator. Okay, so I'd like you to pause the video, try these two examples, find the domain, the zeros, and the asymptotes. Okay, so vertical, which I'm going to abbreviate VA, and horizontal, HA, for both A and B. Pause the video and then come back when you're done. Okay, let's see how you did. So for this one, to get the domain, I'm setting the denominator equal to 0. I end up with x squared equaling -1, which means there's never a 0 in the denominator. There's no way for this to equal 0. So my domain is all reals. Setting the numerator equal to 0, I get x equal to 0, which makes the origin a 0. Vertical asymptotes, there are none. Okay, so these two things always go together. Domain and vertical asymptotes. If my domain's all reals, then I have no vertical asymptotes. And finally, comparing the degrees, they're both quadratic, right, or second power. So they're the same. So this is the case where it's y equal to the ratio of the leading coefficients, 5/1. Okay, for B, we only have a 1 in the numerator, so you can think of the power of x as being a 0. Okay. The domain, x plus 3 equal to 0, gives us x cannot equal -3. So the domain is everything but -3. Make sure you're using your interval notation. For the vertical asymptote, it comes from the denominator. So x is equal to -3. There are no zeros. The numerator cannot equal 0. And for horizontal, this is the case where the degree of the denominator is larger. Because remember, the degree of that numerator is 0. So since the denominator has larger degree, it's the x-axis, or y equal to 0. Okay, again, pause the video. Find the same things for these two problems, and come back when you're done. Okay, let's see how you did. Okay, so we have two values that we have to restrict from the domain, -2 and +1. The x-intercept, 0, 0. Remember, that comes from the numerator. Vertical asymptotes, again, see how these two go together. And lastly, the denominator again has larger degree, so the asymptote is y equal to 0, the x-axis. For D, x cannot equal 2 for the domain. It gives us the vertical asymptote of x equal to 2. The x-intercept, we have none. Again, x squared plus 1 can't equal 0. The numerator has higher degree. It's exactly 1 degree higher, which means we have a slant asymptote. So the slant asymptote is y is equal to x plus 2. And here's my work for finding the slant asymptote. You're doing the long division. It's y equal to your quotient. We can disregard that remainder. Example E, this one we're going to do together. So here, if, let's say, I start finding the domain. For my domain, I know x cannot be 2. Okay, I'm going to find the zeros of the numerator. So this is x plus 2, x minus 2, which means that I would have zeros of -2 and 2. But wait a minute, what's wrong here? We just said that 2 cannot be a part of the domain. How can it be a restricted value and a 0? Well, it's not, right? If you remember what I said from the very beginning, this is important that we have no common factors. When we have a common factor, then the rules change. So let's see what happens. Let's see, do you remember, first of all, from Algebra 2, what happens when we have that common factor? If you said it creates a hole in the graph, that's correct. So what we actually have here is the graph of x plus 2 with a hole at x equal to 2. So this graph would look like the graph of the line, and you could check this out on your calculator or Desmos. It's kind of hard to see the hole. Even on your calculator, you can zoom in as much as possible. I don't think you would see it. But I would graph the line x plus 2. Okay, which is going to look something like that. But, actually let me slide this down. At x equal to 2, I have a hole here. Oops, actually, I'm not even, I gotta slide this up. I was at 1, not 2. And how did I pick up on that? Well, first of all, I could see it, but secondly, I can get that hole by plugging 2 into my equation. So 2 plus 2 is 4, so my hole is at the point 2, 4. Okay. Again, this would be hard to see. I'm not sure about Desmos, but I know on the calculator, if you zoom in, it's really difficult to see. But you could check this on the table. If you go to your table on your calculator, it's going to give you an error for x equal to 2. So the zeros are only 0. Oh, gosh, again, I'm a little bit off here. Sorry about that. Okay. Our only 0 is at x equal to negative 2. And I have no asymptotes. So remember, look for that common factor always, because if you have a common factor, then you're going to have a hole in that graph, okay, at that x value. Okay. So now we're going to put all this together and look at the steps for graphing a rational function. So some of this could be done in different order, but I started off with plotting the intercepts. So we have the y-intercept, right? You're just finding f of 0. So in this case, that would be a negative 1/3. Okay. X-intercepts, we're finding the 0 of the numerator, which is going to be negative 1/2, 0. Vertical asymptotes, so we're going to have a vertical asymptote at x equal to 3. And then we're going to have a horizontal asymptote because the degree is the same. So the horizontal asymptote is y equal to the ratio of the leading coefficients, 2/1. So let's start sketching this. So we have y equal to, or x equal to 3. Let's see, y equal to 2. I have a y-intercept at negative 1/3. X-intercept at negative 1/2. And then what we can do is plot some points. You can use the table on your calculator. You just use your calculator to plug in some values. I'm going to plug in some things that are easy to calculate. Right, so if I'm plugging in, let's say 1, looks like a good number to plug in. That's going to give me 2 plus 3. over 3 minus, or 1 minus 3, which is negative 2. So negative 1.5, which makes sense. And why am I saying that? Because as you do more and more of these, you start to know what's going to happen. But it's still good to plug in some points to get a general shape of the graph. If I plug in 2, then I'm going to get 5 over negative 1, or negative 5. 1, 2, 3, whoops, 1, 2, 3, 4, 5. So you can see how this is starting to soar downward and approach that vertical asymptote. If I go out to negative 2, then let's see, I'm going to have negative 4 plus 1 is negative 3 over negative 1. Wait a minute. I'm sorry, over negative 5, which gives me 3/5. There's a negative squeezed in there, it's hard to see, but let me just check that again. So negative 4 plus 1 is negative 3, and then negative 2 minus 3 is negative 5. So negative 3 over negative 5, which is 3/5. So we're up to about there. Okay, let's plug in one more. How about negative 4? So negative 4 gives us negative 8 plus 1, which is negative 7, over negative 7, which gives us 1. So at negative 4, I'm up to 1. So you can see the trend. It's going to start approaching this asymptote. Will it ever cross it? No, not out at the extremes. When I was talking about crossing, again, that's going to happen in around the origin. Okay, missed a couple points there, but you get the idea. Still working on the curves with this thing, but again, crossing the horizontal or slant asymptote would happen in near around the origin. As it heads out towards negative infinity, it's not going to cross. Okay, I also want to test points on the other side. So if I plug in 4, we're going to have 9 over 1. So you can see it's already way off the graph. So for this one, let's see. I'm just going to put a piece way up here. But you do want to plug in some points, okay, to get an idea of where that curve is, and hopefully it'll fit appropriately on your graph, okay, and not get cut off. Okay, so try B and C, pause the video, come back when you're done, and we'll compare solutions. So find your intercepts, find your asymptotes, plot some points, get some additional points from your calculator, and then smooth out those curves. Okay, let's see how you did. Okay, so I have vertical asymptotes at negative 4 and positive 1, horizontal at the x-axis, and then plugging in some points, I got these shapes here. So you can see this is sort of a parabolic shape. Keep in mind you might also see something that looks like some sort of cubic curve. So there's lots of possibilities when you have 2 vertical asymptotes and 3 sections of the graph. That's why you need to test those points and see where those curves are going to be located. For C, I have a y-intercept of 2, vertical asymptote negative 1, horizontal at the axis, plotted some points to get a better idea of where the curve is. Okay, so again, try these 2, pause the video, and then come back when you're done. Okay, let's see how you did. Okay, so I factored the denominator. So we're going to have 2 vertical asymptotes again, right? X equal to negative 3 and x equal to 1/2. Okay, our y-intercept is negative 1/3. X-intercept at negative 1, which I think I'm on the wrong side there. that was meant to be -1 over here. Okay, and then I did a little bit of cheating and did it on Desmos. Okay, so you can see what happens here. Here's that piece that looks like a cubic curve in between the two vertical asymptotes. And then we have the two outer pieces of the curve. So again, that comes from plugging in values and testing points. For letter E, the numerator has higher degree than the denominator, so we're going to have that slant asymptote. I came up with y equal to x plus 2 for the slant asymptote. There it is. We have a y-intercept of -2.5, an x-intercept of -2. Which did I put? I'm sorry, what am I saying? X-intercepts of plus or minus √5. Okay, that's what these points are here. Okay, vertical asymptote at x equal to -2. So when we put all that together, plot some points, you should end up with two curves that look like this. And you can see with that line of x plus 2, was it? Oops, or was it -2? There we go. X minus 2. Did I have that? Let me go back and check. Why did I have a... Oh, darn it. This is a minus... What did I have here? +2. You have to change those signs. So that's a -2. I apologize. Okay, so if you were questioning, wait a minute, I got a slant asymptote of y equal to x minus 2, you were correct. I made a mistake. I didn't follow one of my own rules that I always do, is I change that sign and I circle it. And I didn't do it that time. And see, I missed it. So, let's see. Let me just double check this. So we're dividing, distributing x squared plus 2x, so that becomes minus, that becomes minus, so it's a -2x minus 5, so it's -2. So the slant asymptote is y equal to x minus 2. Okay, so let's take a look again at the graph. So there's that line. You can see how it's traveling along it as x heads out to infinity, and it's traveling along it as x heads out towards -infinity. Okay, so that concludes the lesson for 2-6. I hope you enjoyed it, and I will see you in class. Have a good day.